That means you could order in-store products at in-store prices while you're in sweatpants, in spin class, in stuffy work meeting, in anywhere but in-store.
Credits. Own your own home and need a loan? Alpine Credits can help. Visit alpinecredits.ca.
Hey, it's Laura Lichtman, and you're listening to Science Friday. Today in the show, how a mega popular reality show upended what scientists thought they knew about metabolism.
I was interested in participating as a researcher, observing these folks who were doing this sort of natural experiment, a study that couldn't have been done otherwise had they not already been signing themselves up for this kind of abuse on a national television show.
Remember The Biggest Loser? That show where people tried to lose as much weight as quickly as possible for a big cash prize. The premise of that show was that weight loss was about willpower. With enough discipline, anyone can have the body they want.
Do not be sloppy. Finish this strong, Joelle. No, Joelle, don't do it. Don't do it. Dig, Joelle, dig.
The show had issues, and it hasn't aged well. And while the weight loss landscape has gotten more complex with GLP-1 drugs like Ozempic and Wegovy, a social media-fueled wellness industry, infinite fad diets, the underlying idea that weight loss and health is as simple as move more, eat less, hasn't gone away. But does that match current research? How is our understanding evolved? But a new book written by a journalist and a nutrition scientist who, among other things, studied Biggest Loser contestants, breaks down the science of nutrition and metabolism and what we've learned in the 2 decades since that show premiered. The book is called Food Intelligence, and I want to bring on the authors, Dr. Kevin Hall, nutrition scientist and former NIH researcher based in Kensington, Maryland, and Julia Balouz, science journalist based in Paris. Welcome to both of you to Science Friday.
It's a pleasure to be here.
Thanks for having us.
Okay, let's start with this. What is food intelligence?
Well, the title's really a play on the idea that people really have a, pun intended, hunger for knowledge about what it is that they're eating and how it works inside their bodies and what it means for health. And so the idea of the book is to provide people with the necessary background about the science of nutrition and metabolism and give them some intelligence about the foods that they eat.
Is the idea that we are all born with a sort of innate understanding of what our body needs?
This was, as a layperson, this was one of the most surprising things in reporting this book, that we are all as living things equipped with this symphony of internal signals that guides our eating behavior to a much greater extent than many of us realize. And what we found in the book is that modern food environments have interrupted that system that has served humanity quite well over many, many thousands of years.
Modern food environments such as ultra-processed foods, fast food.
Exactly, yeah, the kind of foods that many Americans in particular are surrounded by now.
Julia, what drew you to writing about nutrition and food?
So I'm someone who struggled with my weight. I was a chubby kid and teenager, and my weight fluctuated up and down, including having obesity. So I'm someone who struggled with my weight, and I'm Canadian. And when I moved to the US, there was this time when obesity rates were soaring as they are now, and I became curious, why is it that so many people are like me? They seem to know what they should be eating, they want to be eating better, but they can't, or they struggle to. And in that reporting, I got to know Kevin, who was doing this fascinating research on kind of many different areas of nutrition science. And when I would talk to him, so much of what he was saying was so disconnected from where the public conversation was at. As it is now, there was a lot of conversation about fat diets or supplements or various supposed panaceas for people's weight and diet struggles. And then when I would talk to Kevin, that the solutions were really different. It seemed like bariatric surgery was the only effective tool we had for dramatic and long-term weight loss at the time. The GLP-1 drugs were already coming onto the scene. They were being used for diabetes, and people were seeing weight loss in those trials. But the public conversation still fixated on these kind of individual hacks and fixes that scientists like Kevin appreciated for most people in the current environment just didn't work.
Kevin, I want to talk about some of your research. I mean, you worked at NIH a long time, but there's this interesting Eddie, your resume, where you worked as a scientist on set on the TV show The Biggest Loser. What were you doing?
Yeah, so that's while I was still at NIH, and I was really interested in understanding what was happening to these folks. This was a very strange lifestyle intervention that was televised on national TV for many, many seasons. And these folks were, subject to a whole lot of abuse, but in the space of that abuse, they were doing a ton of exercise, different kinds of exercise. And it wasn't clear how that crazy lifestyle intervention was influencing their bodies in terms of how much of the weight that they were losing was coming from body fat versus muscle, for example, or whether or not their metabolisms would slow down, as typically happens with diet programs that don't involve a lot of exercise. There was a lot of discussion back then that exercise would boost metabolism, and therefore you wouldn't experience the usual metabolic slowing. So I was interested in participating as a researcher, observing these folks who were doing this sort of natural experiment, a study that couldn't have been done otherwise had they not already been signing themselves up for this kind of abuse on a national television show.
What did you learn?
Yeah, we learned that many of the things that we had presumed about exercise and about metabolic slowing didn't turn out to be true. So despite the fact that these folks were engaging in roughly 3 hours of vigorous exercise every day of the week, their metabolic rate did slow down by as many hundreds of calories per day on average. But maybe most surprisingly, it was the folks who had the greatest slowing of metabolism who lost the most weight. And this was a trend that we saw kind of 6 years later when we brought these folks back to the NIH Clinical Center to study them 6 years after the lights of the television cameras turned off. Most folks had regained most of the weight, or at least 2/3 of the weight that they'd lost on the program. Some people regained all of it and more. One person continued to lose weight, and one of the things we were interested in was whether or not the metabolic slowing at the end of this crazy competition predicted who would regain the most weight, as had been assumed to be the case in previous hypotheses. And again, we had a surprise that there was actually no relationship between the folks who had the greatest slowing of metabolism after weight loss and the subsequent weight regain. And in fact, once again, 6 years later, the ones who were most successful at keeping the weight off, they boasted the slowest metabolisms.
What does that tell us about our understanding of metabolism?
Well, it tells us that metabolism isn't driving the cart here, right? It's actually something else that it's following. It's more the cart than the horse, and I think that's a new way that we are beginning to think about this. It's not determinative of body weight change in the way a lot of people like to think when they say, "Oh, I just have a slow metabolism, and that's the reason that I might be heavier than I would like to be." It's more complicated than that, and in fact, the metabolism seems to be responding responding to the lifestyle interventions that these folks had experienced, and it responds in proportion, so that if you do more changes in your diet and exercise, metabolism will respond, but you'll also receive the greatest amount of weight loss or maintenance of weight loss.
So it's not the metabolism that's driving the weight loss, is what you're saying.
Right. The way that we say it in the book is, it's not metabolism, stupid.
Perfect. That's right at my level. Thank you, Kim. Julia, in your quest to better understand metabolism, you hermetically sealed yourself into a metabolic chamber. Please tell us about this experience.
So part of this quest that I had to understand, why was I a person who struggles? Why do so many of us struggle with our body weight? The first place I actually turned was having my metabolic rate measured in this metabolism chamber at NIH. And I was quite sure that this must be one of the reasons. I was someone who had, found it difficult to keep my weight down and had to put a lot of conscious effort into it. And as it turns out, my metabolic rate was completely normal for someone my age, gender, and body size. So this did not explain anything, and that obviously led to more questions than what was it. And in the process of reporting on the book, I had my genes analyzed as well, and I found out I am at a much higher risk for both obesity and diabetes than most of the population. But all the researchers I spoke to, including Kevin, said, genes for most conditions, they're also not determinative unless you have, like a rare single gene disorder or something.
We have to take a break, but don't go away, because when we come back, how much protein should we really be eating?
For most folks, they already get pretty close to double the recommended daily allowance.
Vermont listeners will be in Burlington on Friday, October 17th for a live Science Friday stage show. We're digging into the future of food, and we'd love to have you at the table. Join us. Tickets are at sciencefriday.com/Vermont Live. We also had tons of questions from listeners who had just many queries about nutrition and diet. So let's go to the first one.
This is Mary Kay. I'm calling from Florida. I'm 73, and there's a lot of information about how much protein I really should be eating to not be losing muscle mass and all those good things. I would love to know what the really latest information is on how much protein we need at different ages. Thanks so much. Love your show.
So that's a really interesting question, because I think that the amount of protein that people should be eating very much depends on the stage of life that they're in, and whether or not you should be worrying about it also depends on the stage of life. So for example, in folks who are older, who are likely to be in settings that have reduced protein availability and are at risk for losing a lot of muscle mass, then people seem to think that increasing the amount of protein from the recommended daily allowance is a good idea. We talked to a protein researcher in reporting for the book, Stuart Phillips, who makes a very poignant case that folks who are elderly and in institutional settings in particular are particularly at risk for losing muscle mass and losing mobility, and he recommends that people eat double the recommended daily allowance. For most folks, they already get pretty close to double the recommended daily allowance, and they shouldn't be worried too much about the protein content. If you're worried about muscle mass, and this is true across the board, the best thing that you can be doing is resistance exercise.
Pick up some weights. Is that what I'm hearing?
That's exactly right. Pick up some weights, get active, do some of that work, because that's going to have much more bang for your buck than any increases in these protein supplements in particular that people are using.
Like, I don't need to have a protein cold foam from Starbucks.
Not likely. Not likely. It's probably defeating the purpose with all the sugar and whatnot that's probably being added to it.
We got another related question from Nicole in California.
My question is, I heard that if you just eat a lot of protein and you don't use it through exercising or moving your body, that it just turns into fat. does protein turn into fat if it's not used?
Yeah, so I mean, I think that this is part of the idea that well, number one, the protein that you eat is being broken down in your gut, and those kind of building blocks, those amino acid building blocks, are being create other proteins inside your body. It's not just about muscle, and it's not just about powering muscle. Certainly, that was the debunked idea from the 19th century. The idea here is that you can overeat protein, and that protein that's not being used will be essentially, those fuels will be used to fuel metabolism. And if you're eating excess calories, certainly you will then gain body fat. And we outline the pathways that happens in the book, and some of the really interesting shifts in the fuels that the body is using when you're eating protein and fat and carbohydrates in the diet, and how that all works out in the end to, if you're overeating calories, and those extra calories end up as body fat.
You know, we get a lot of questions about fad diets, and it feels like every diet has some special formula of fat, carbs, protein that we should be shooting for. Are there actual guidelines backed by science that work for most people about the correct ratio of those food groups?
Yeah, no, one of the things that people get confused about is that typically there's this ongoing back and forth debate about the evil nutrient, right? Protein seems to have been mostly spared in that discussion, but whether or not it's the dietary fat that makes you fat or the dietary carbs that are making you fat seems to have flip-flopped depending on whether or not low carb or low fat diets are the most popular fat diet of the era. And one of the things that we've done in our research is to try to better understand how does the body use carbohydrates and fats, and in particular, how does the body shift its fuel usage when you make very large swings in the ratio of carbs and fat in the body. And our research, and as well as many other people's research over the years, have really shown that carbs and fat, despite being pitted against each other in these diet wars, are really like good colleagues. They kind of stand in for each other when the other one's out. And the idea here is that we're omnivorous species. We can thrive on a wide variety of different diets, and the body has been evolved in such a way as to choose the fuels that it's using based on the ratio of carbohydrate and fat in the diet, and either one can do its job. And if you're consuming excess calories, either in terms of higher amounts of carbohydrates or higher amounts of fat, almost identical amounts of body fat will be changed. So that goes for also the deficits as well. If you're eating too few calories to maintain your weight, it doesn't matter much whether or not that's a low carb diet or a low fat diet.
Okay, last question. Whether dopamine is the culprit in ultra processed foods, or not, you both point to our food environment, ultra processed foods, as problematic. What would it take to actually loosen the grip of ultra processed foods on our diet?
We describe in the book how we're basically in this total inversion of the food environment that we should have. So the worst for you foods are the most accessible, available, affordable, easy to put in your mouth, basically. And the best for you foods are the hardest to come by, and they tend to cost more. And so yeah, we call for basically an inversion of this food environment, and also meeting people where they are. So that means giving them these prepared, healthy, sometimes even processed options that they can eat easily if they don't have the time, wherewithal, or desire to cook.
What we think we need to do is make changes in policy and regulations to, first of all, target the ultra processed foods that are potentially the worst players. That should be based on science and the mechanisms by which we think that those ultra processed foods are playing a role in driving diet related chronic disease. And then there's a whole suite of policy changes that one could make in order to reduce the prevalence of those foods, but in addition, and most importantly perhaps, make make the healthy alternatives, some of which might actually be ultra processed healthy foods. That's not really an oxymoron, really, believe me. And if we could make those healthy alternatives equally convenient and compelling and readily available to folks, that's the path forward.
Julia Ballou, science journalist based in Paris, and Dr. Kevin Hall, nutrition science. Hey, it's Flora Lichtman, and you're listening to Science Friday. On today's episode, the science of replacing body parts, from hearts to hair.
If you take armpit hair and put it on the head, this is a quote from some clinic in LA, it is difficult to style.
It seems like every week there is a new headline about some kind of sci-fi sounding organ transplant. Eyeballs, 3D printed kidneys, pig hearts. In the new book, Replaceable You, Adventures in Human Anatomy, science writer Mary Roach chronicles this effort to fabricate human body parts and why it can be so monumentally difficult. The book does not skimp on the details. So if you want to hear the nitty-gritty on hair transplants or today is your day, and if you don't say we didn't warn you. Mary, welcome to Science Friday.
Thank you, Flora.
This is your 5th book on the human body, I think, if I'm counting right. It's a characteristically wild ride. What keeps you curious about our bodies?
Well, they're just endlessly amazing and weird, I think is the answer. I mean, because I didn't study biology or physiology in any formal way. Every time I step into a new system of the body, whether it's the alimentary canal, because I'm just going on behind the scenes, behind the curtain. It's kind of miraculous and weird.
Behind the skin drapes, yeah.
Yeah, skin drapes, exactly.
Mary, let's start with a transplant that weirdly is dominating my social feeds right now. Hair transplants. What is the state of hair transplants?
From the sides or the back of the head where they're not sensitive to testosterone, they're not going to fall out. You put those on the top of the head. Now they're going to stay permanent. They're going to fall out because they retain the characteristics of the back of the head, side and back of the head hair.
They've got that back of the head hair identity.
Yeah, exactly.
Yeah,
exactly. So that's kind of the principle of it. But over time, of course, if your hairline recedes and it continues behind where the new transplants were, now you're going to have a bare patch there. So it's kind of an ongoing relationship between the surgeon and the patient. And I looked into the history of hair transplants. It began with this surgeon named Okuda, a Japanese surgeon, and I found the Okuda papers, and he was going crazy with the donor dominance. He was like, you can take chest hair, you can take armpit hair, put it on the head, you can take head hair and put it use it for pubic alopecia, which I had never heard of, but apparently it is something that can happen. But
that's such a you book thing, Mary.
I know, the Okuda papers, I was like, wow, he did that. He was like putting armpit hair on the mustache, and anyway, but then it works. It all works. The issue again with donor dominance is that, say you had head hair in the pubic region, now you need to trim it. If you take armpit hair and put it on the head, this is a quote from some clinic in LA, it is difficult to style.
You did some self-experimentation for this book.
Yes, I did. Well, when I went out on book tour, I wanted to be able to demonstrate donor dominance. So I was at a hair transplant clinic in Southern California, and I asked if they would transplant a follicular unit from my head to my calf, so that during the book tour I could roll up my pant leg and just show them this long, luxuriant hair that was growing on my leg.
A leg pony. Yeah.
Yeah, exactly. You know, and then it had I think it had two follicles in it, so it would have been 2 hairs, long, flowing hairs. Unfortunately, it didn't take.
But they did it. Like they did. Like, oh, sure, we'll do it on our lunch break.
Yeah. Well, what happened? I was donating a dozen follicles to science. So they were studying just the process by which follicles grow. You know, from the basic cells, keratinocytes and dermal papillae cells. How do they grow into a follicle so they could try to match that? So I said, sure, I will donate a dozen hairs to you and your effort. I have now a little tiny bald spot.
Itty bitty.
Yeah, at the top of my head. And I said, well, while you're doing this, would you mind putting a few in my leg? I explained I really want to be able to demonstrate donor dominance. This is educational. It's
anything for psychoms.
Yes, exactly.
As we say.
Exactly.
Let's talk about Judy. Tell us about Judy.
Oh, sure. Yeah, Judy is, she's kind of the starting point for this book. She's a reader who wrote to me going back almost 4 years now and said, I love your books, and would you write one about professional football referees? I don't know why she thought that was a good fit for me. I don't watch football. I don't know anything about football. But anyway, in the course of emailing back and forth with her, she mentioned that she's an amputee, specifically an elective amputee. It was an elective amputation. She had spina bifida. Because of a tumor spinal cord, her foot was twisted. She wasn't able to walk on it the way she wanted to be able to walk on it. She'd had numerous surgeries that weren't really resolving the problem, and she would see people with a prosthetic lower limb who were hiking and running and doing the things she couldn't really do. And she was trying to find a surgeon to cut off her foot.
Trying to find a surgeon, because it was hard to find a surgeon.
It was hard to find somebody, because they'd say to her, well, this is a healthy foot. It has a blood supply. It's not gangrenous. You could just get more surgeries. And it took her years to find someone to do the amputation. And it's an interesting issue. There are reasons why surgeons don't want to do that.
Such as
what if there's phantom limb pain? What if the patient sues me? I can't put this foot back on. It's just safer to say, let's try one more surgery. Safer in the sense of, am I going to help this patient or make things worse? Because there's a certain finality to cutting off a foot. It's also, you need the insurance to cover it, unless the patient wants to pay for the surgery out of pocket. So you would need to make the case that this is necessary, medically necessary. And if the foot is not dying, that may be hard to do.
Right. In this chapter, you write about this bias that we seem to have towards wholeness, that the whole body is better than some incomplete body. And as I was reading it, I was thinking that culturally, in other ways, we do accept body modification all the time. Botox, collagen, rhinoplasty, and then sometimes we don't at all. And I wondered what you made of that.
Well, I think we accept it if it's making much when it's perceived as a disability. Limb salvage surgery, in other words, let's keep the foot, just do surgery after surgery after surgery and try and get it to the point where almost as good as new. Versus, let's be realistic, this is unlikely to get to 100%. Let's amputate now, and the person will ultimately be better off in terms of discomfort and function. And time and again, things land on the side of amputation. But I think because it feels drastic, no matter how problematic that foot has been, it's you, and it's gone. So, and I think that particularly as an outsider, imagining that when you're not dealing with the discomfort and the pain of this foot that doesn't really work well, you can't imagine that. You put yourself in that position.
The book is filled with, what was your favorite replacement from the book?
My favorite replacement, well, I found fascinating the ones in which some part of the human body is asked to become a different part. And there were a number of those. The body is very flexible, agreeable, you might almost say. I had dinner with a surgeon at Cedars-Sinai Center for Transgender Health and Surgery. And one of the techniques that is sometimes used is not a it's not a common first approach, but to create a neo-vagina for a trans woman, you can take a section of the ascending colon, I think it was, and you can keep it attached to a blood supply and kind of use it as a vagina, and then also do vulvoplasty. So you have all the sort of outside components, but that's something dating from the 1800s. There were patients who'd had cancer, and there were a couple of surgeons who had tried that, and it does work. Another one that was fascinating to me is that you could use the rectum as kind of a third lung.
That.
If you have an infant born very, very premature, so their lungs haven't developed to the point where they're really working, that it means that you're going to have to go on the neonatal intensive care unit, and to use a ventilator, a positive pressure ventilator on an infant that young, it can damage the lungs. So if you could augment with material through the rectum, which you can, the mucosa will absorb oxygen that way, then you get a boost.
You can breathe through your butt.
You can breathe through your butt is what I'm saying.
That is an aha, I would say.
You can breathe. Somebody told me about that, and I'm like, so it's going all the way through. That's just like constant copious farting then, like that. It's not, that doesn't
on babies it's cute.
It's cute. Exactly. They get away with it. Yeah,
that's right. Hey, don't go away, because coming up after the break, just how close are we with 3D printed organs?
We're kind of in the Wright brothers era if you compare it to flight.
Let's talk about lab-grown organs. Where are we with that?
Bioprinted organs, I asked that exact question. I was at Carnegie Mellon, the Feinberg lab, where they're doing some very cool stuff, printing muscle in particular, and it's so much more complicated than you would think. It's not like printing 4-color brochure. And I said to Dr. Feinberg, well, how long before we're at the point where we can print an organ that can be installed? And he said, we're kind of in the Wright brothers era, if you compare it to flight.
But that's a big era,
Yeah, and things happened fast between Wright brothers and plane flights, right? But it's pretty quick, and so stuff is moving. I mean, he said a couple of decades. And to me, that sounds slow because, to me, that's like 3 or 4 books. Whoa, that's not fast. But he's like, things are moving very quickly, 2 to 3 decades. No. So with printing muscle, it's fascinating. You have to align the cells so that they will perform the function for which that muscle was intended. For example, the heart, and I didn't know this, when the heart squeezes blood out, it twists slightly, kind of like wringing out a sweater. You get the maximum amount of blood expelled from them, via the musculature contraction. So if you're printing a heart, say, or a ventricle, that you print them in like a helix form, as opposed to, say, a hamstring muscle where they're kind of parallel. So you don't really think about that. Plus, you got to feed that muscle. So are you going to print the vasculature? You're going to, they're at the point where they're trying to figure out, okay, how much can we let the body do? Because the body will grow in capillaries. So some of it you can get the body to do, but at a certain point you're going to have to print those. Nobody's printing nerves quite yet. So.
And should I be imagining a 3D printer, or is this more like a Chia Pet, where you have some kind of scaffolding and you sprinkle the
No, what I saw is it's a printer with like 4 extruder heads that can be printing different material, like cellular material in one, extracellular like collagen material in another one. So it's laying down one layer at a time. So it's a printer. Feinberg teaches a course where you can take like a Office Depot printer and you can kind of like rejigger it to make a 3D printer. So obviously, for simpler things than hearts, but it's a printer.
I'm assuming the best option for transplants is there's still organ donors, though.
Yeah. Yes, the best option is right now still a human donor's organ. One of the things going on that I found kind of exciting, because it's a little bit simpler than printing something or growing it from scratch. At the University of Michigan Extracorporeal Life Support Laboratory, extracorporeal meaning outside the body.
It's a great name for a lab.
It is, totally. So one of the things they're trying to do is extend the shelf life of a donated organ, like a heart, say. Okay, the traditional method where you put it on ice and you ship it out, you've got 4 to 6 hours to get it where it needs to go. But they're looking at tweaking that so that they can extend it to a few days or more, which would be very cool, because you could now bring in a echocardiogram machine and take a look at the heart, see how it's pumping, how well is it, how healthy is that heart, and if there's an issue that could be fixed, you could fix it. So right now, there's an age cutoff, because you don't have time to take a look and see how well it's working. You basically say, well, these are too old, so we're not going to take them. But if you could do it based on quality, that'd be helpful. And if you could repair them, that would also be helpful.
The title of the book is Replaceable You. Do you feel like we are replaceable, or our parts anyway?
No, the title really should be Irreplaceable You, but it doesn't sound as good, because it's a play on this song that, of course, nobody who's younger than 40 is going to know. Embraceable You. It's some old kind of standard from way back when that I happen to have heard of. But yeah, it should technically, the book should be called Irreplaceable You, because I don't, I tried to find just what's a simple bit of the body is there anything simple that we can replace so that it's 100% as good as what you were born with? And I thought about, okay, tears, that seems pretty straightforward, like salt water, a little bit of oil to keep it from evaporating. How hard can that be? And I contacted this researcher who has studied tears for decades. And, we went on for 2 of the free Zooms, because I'm too cheap to pay for Zoom. We went on for 2 45-minute Zooms about the tear film. And I said, so artificial tears that you buy? He goes, well, yeah, those will buy you, a couple of hours, but they kind of wash away the good stuff. So, no, they're not a replacement. We as a species have gotten pretty good at coming up with substitutes when things go wrong. But in terms of plugging in something that is as good as what you started out with, I can't name one.
Mary Roach is a science writer and author of the new book, Replaceable You, Adventures in Human Anatomy. Thanks for coming on, Mary.
Oh, thank you so much. That was really fun.
Really fun. Hey, I'm Flora Lichtman, and you're listening to Science Friday. On the podcast today, a conversation from our live show in Redwood City, California. We're talking about one of the most profound questions in science. How did life begin? I want you to sift through your memories and excavate an image of a fossil. Maybe you're picturing dinosaur bones, or an imprint of an ammonite, or the fronds of a fern etched into stone. But there's a whole other category of fossilized remains that can tell us about life way before T-Rexes or even twigs existed on this planet. I present to you fossil microbes. Well, technically, the fossilized evidence of them. My next guest uses these ancient remains to understand how life began on Earth, which may also help us find life elsewhere in the universe. Joining me now is Dr. Paula Welander, Professor of Earth System Science at Stanford University. Paula, welcome to Science Friday.
Thank you.
How How do microbes show up in the fossil record? Like, what are you looking for?
Like you said in introduction, when we think about a fossil, we think about like Jurassic Park, right? The dinosaurs. Those are morphological fossils, and those are usually hard structures. But microbes are soft, right? They're single-celled, and so a lot of their tissue is what we consider tissue gets dissolved in the process of rock forming and fossilizing. So geochemists had this idea to extract organic molecules from these fossilized rocks, and a whole slew of chemicals came out and turned out to be molecules that microbes make. We also make them, but that can be preserved in the rock record. And these are primarily like fats, lipids.
So
structure.
not rock.
Yeah.
Very clearly not rock.
Yes, not rock. And over the years have developed different like techniques, instrumentation that allows them to pull these molecules out of the rocks and identify their structures, their chemical structures. So they're chemical fossils. And it's exciting because then you don't need a hard morphological fossil, and you can get interpretation of what is actually being deposited at the time.
I'm going to nerd out a little bit here. What makes lipids good at preserving?
So lipids are really important. So you all know cholesterol, right? We all have cholesterol. It's bad for you. It kills you. No, we need cholesterol, and that's a lipid. It's one of the macromolecules that sustain life. And these lipids for microbial organisms are their external barrier from the environment. So it makes them resistant to a lot of the stresses they might encounter, say in a hot spring, right? And what we have found over time is that microbes that live in these environments that can be very extreme have modified their membrane lipids so that they can withstand high temperature, low pH. And those structures are then preserved in the rock record. So if you look back deep in time and you see a specific structure that we see microbes making in a hot spring, you can make the connection between that ancient environment and this modern environment because the lipid molecules are the same. So those are preserved over billions of years.
Wow. Okay, so tell me about the extremophiles you study that give us this window into the past.
So the organisms that we work with primarily are usually they're found in hot springs, but they can also be found in hydrothermal vents. They can be found in like mud volcanoes that are really high in methane. These types of organisms can require high temperature, low pH, and extremes of different kinds in order to be able to survive. They need that. So for example, the stress for this organism, it normally grows at like, let's say 75 degrees Celsius. I don't know what that is Fahrenheit, like 200 Fahrenheit?
Hot.
Yeah, very hot. You bring it down to like 100 degrees Fahrenheit and it dies because it needs to go at that temperature because it has evolved not only its lipids, but its other macromolecules to be able to thrive in that environment. So these environments are really exciting to go find these microbes because they push the edges of what we consider life, of what we consider how we survive in an environment. They really push chemistry.
Do you physically go out to the field and scoop them up?
I don't. So I'm a brat. I like to work in the lab. We can actually grow these in the lab. And so there are people that go out and do that. I've had grad students who want to go do it, and they go into the environment and they pull them out. And they'll take new organisms and we'll grow them in the lab.
So you particularly would rather be in the lab?
Yes.
Like people in your lab go out?
Yeah.
These fossilized remains of microbes, I mean, how far back in time can you go?
We can go back as far as 1.8 billion years ago.
Whoa.
Yeah. Which, honestly, I know seems like very, very old. To geologists, is not that old because the planet is about 4 billion years old. Life's been on this planet for about 3.8 billion years old. So geologists wish we could go all the way back there, but that process of preservation doesn't go back. These are definitely the oldest fossils we can find.
And what are you learning about this time period that we didn't know before?
So we're learning one of the key important things about the Earth in the past is very different than the Earth is now. For example, for the first 2 billion years that the Earth was in existence, there was no oxygen, like at all. And now we are 20% oxygen. So how did that happen? That turns out that microbes have interacted with the Earth. Microbes invented the ability to do what we call oxygenic photosynthesis, what plants do, and generate oxygen and oxygenate the Earth. So what we learn when we study about these microbes deep in the past is when did that happen? Geologists are very interested in when that happened and what are the markers that we can see in the past that can let us know, like, oh, this is when it happened. And you can see that the chemistry of the earth changed. And this idea that the evolution of life, so the ability for microbes and life to impact the earth, is also impacted by the evolution of the earth, because the earth is also changing from processes that are not involved in biotic mechanisms. So it tells us a lot about how this push and pull happens between the evolution of life and the evolution of earth. But it also tells us about a lot of perturbations in the past. For example, we can see times when the earth was completely covered in ice and was really cold, and we can see how the microbes changed over time at that stage.
And you can see that in the lipids?
You can see, well, the lipids actually help determine that state, right? Because we can see that the lipids are a certain, it's interesting because, you know, the way geologists do this is they have stratigraphy, right? And each layer of a rock represents a certain age and time. And you'll see blips of, like, you know, the lipids are low and then they go up and then they come back down. And they can see where those changes are happening. But that's like 100 million year time scale.
What do these Earthling extremophiles tell us about possible life on other planets?
So we basically need to understand how life might evolve, right? So how might life have evolved, and what are the signatures, what are the markers that we can find in that? So a lot of study of the origins of life is focused on understanding how it occurred on this planet, because this is the only planet we know where life has actually originated, right? Where it's evolved. And then what are the signatures that are left? We know that the first forms of life were microbial. They were definitely single-celled organisms. And if we look deep in the past at these rocks, what are some of the molecules that we can find? Because if we go, say, to Mars or the moons of Jupiter, and we are able to pull a sample, what do we look for in order to be able to find there? So if you find molecules that are preserved, that are similar to what we see in the past here on this planet, you can start to make that connection.
Is it possible that we don't know what to look for?
Exactly. That's the challenge, right? We're kind of biased, right? We're trying to, there's this idea of life as we don't know it, right?
Right.
And so that is a little bit having to be open-minded and thinking about what are some other signatures we might be able to find. But we're scientists, we're grounded in what we do know. And I think fully understanding the possibility of life, both in the rock record and in the lab, will allow us to think creatively about what we might not be able to see right now.
Okay, while I have you, there was some exciting news just a couple weeks ago about a possible biosignature found on Mars. I feel like these stories happen kind of regularly. Was this one, how hyped were you for this one?
Well, I love the Mars rover stories because they really exemplify what we can do when we come together as scientists, as a community. The number of people it takes to do those kinds of projects is insane. In the years of planning, years and years. And so to see it come to fruition is really, really cool. So what we saw was these iron phosphate, these iron being made that can be signatures for microbial life. It can be the waste products of microbes that get preserved in rocks, but there can also be, you know, non-biogenic sources of this. So for example, when you think of, like, when we breathe out CO2 as our waste, right? So CO2 can be a biomarker for life, but you also get CO2 from volcanoes, so it can be a biomarker for marker for volcanoes. The same thing with these iron minerals. But I think what we really need is to be able to bring those samples back. And I really hope that return mission is not cut from NASA's funding, because that's the most exciting thing. To be able to bring these rocks back up the rover and put them under our machines here would really be exciting to study.
Yes, that would be amazing. Let's go to the audience. Let's go here.
When studying these ancient microbes, what information isn't in the fossil record? You know, in the same vein as dinosaurs and feathers. What are your blind spots? What are you not seeing?
So I think the hard things to see is what exactly the microbe was, the metabolism that it did. So when we talk about metabolism, microbes are really cool because they can eat almost anything and they can secrete almost anything. You know, we eat sugar, you know, and we breathe in oxygen and we spit out CO2. That's all we do. We're pretty boring metabolically. But microbes will, like, eat arsenic and they'll eat like iron. And so I think a lot of times what we're missing is what are the structures, the proteins that are involved in that process. We see the beginning and the end, and we miss what's in the middle. And that, for me, being like a protein biochemist, is the most exciting part. So those are some of the blind spots that we have.
I mean, so you're a basic scientist. Have you had to justify your work in recent days?
I always have to justify basic science, but not in the current environment. I mean, I think for me, like the ability to discover has been always the draw to science. The ability to bring in new knowledge, is irrelevant as it may be to everyone in the world. Me discovering a new protein that makes a new lipid is always super, super exciting. But we always, like many of my fellow academics, I am funded by the government. I have federal grants, and I fully believe I do need to justify that to the taxpayer. What am I doing with your money? And I'm funding students and scientists in my lab to carry out this research because we don't know what we're missing, right? We don't know what we don't know. And so just wanting to study the world and understand the physical, biological world that we live in is so important to give us all the wonderful discoveries and advancements that we've made over the years.
Well, thank you so much for being here. This is fascinating.
Thank you. Thank you.
Paula Wielander is a microbiologist at Stanford University. Thanks for listening. Don't forget to rate and review us. And you can always leave us a comment on this segment on Spotify. We'd love to hear from you. I'm Flora Lichtman. Thanks for listening. Hey, it's Flora Lichtman, and you're listening to Science Friday. Today in the show, how a mega popular reality show upended what scientists thought they knew about metabolism.
I was interested in participating as a researcher, observing these folks who were doing this sort of natural experiment, a study that couldn't have been done otherwise had they not already been signing themselves up for this kind of abuse on a national television show.
Remember The Biggest Loser? That show where people tried to lose as much weight as quickly as possible for a big cash prize. The premise of that show was that weight loss was about willpower. With enough discipline, anyone can have the body they want.
Do not be sloppy. Finish this strong, Joel. No, Joel, don't do it. Don't do it. Dig, Joel, dig.
The show had issues, and it hasn't aged well. And while the weight loss landscape has gotten more complex with GLP-1 drugs like Ozempic and Wegovy, a social media-fueled wellness industry, infinite fad diets, the underlying idea that weight loss and health is as simple as move more, eat less hasn't gone away. But does that match current research? How has our understanding evolved? A new book written by a journalist and a nutrition scientist who, among other things, studied Biggest Loser contestants, breaks down the science of nutrition and metabolism and what we've learned in the 2 decades since that show premiered. The book is called Food Intelligence, and I want to bring on the authors. Dr. Kevin Hall, nutrition scientist and former NIH researcher based in Kensington, Maryland, and Julia Balouz, science journalist based in Paris. Welcome to both of you to Science Friday.
It's a pleasure to be here.
Thanks for having us.
Okay, let's start with this. What is food intelligence?
Well, the title's really a play on the idea that people really have a, pun intended, hunger for knowledge about what it is that they're eating and how it works inside their bodies and what it means for health. And so the idea of the book is to provide people with the necessary background about the science of nutrition and metabolism and give them some intelligence about the foods that they eat.
Is the idea that we are all born with a sort of innate understanding of what our body needs?
This was, as a layperson, this was one of the most surprising things in reporting this book, that we are all as living things equipped with this symphony of internal signals that guides our eating behavior to a much greater extent than many of us realize. And what we found in the book is that modern food environments have interrupted that system that has served humanity quite well over many, many thousands of years.
Modern food environments such as ultra-processed foods, fast food.
Exactly, yeah. The kind of foods that many Americans in particular are surrounded by now.
Julia, what drew you to writing about nutrition and food?
So I'm someone who's struggled with my weight. I was a chubby kid and teenager, and my weight fluctuated up and down, including having obesity. So I'm someone who struggled with my weight, and I'm Canadian. And when I moved to the US, there was this time when obesity rates were soaring as they are now. And I became curious, why is it that so many people are like me? They seem to know what they should be eating. They want to be eating better, but they can't, or they struggle to. And in that reporting, I got to know Kevin, who was doing this fascinating research on kind of many different areas of nutrition science. And when I would talk to him, so much of what he was saying was so disconnected from where the public conversation was at. As it is now, there was a lot of conversation about fad diets or supplements or various supposed panaceas for people's weight and diet struggles. And then when I would talk to Kevin, that the solutions were really different. It seemed like bariatric surgery was the only effective tool we had for dramatic and long-term weight loss at the time. The GLP-1 drugs were already coming onto the scene. They were being used for diabetes, and people were seeing weight loss in those trials. But the public conversation still fixated on these kind of individual hacks and fixes that scientists like Kevin appreciated for most people in the current food environment just didn't work.
Kevin, I want to talk about some of your research. I mean, you worked at NIH a long time, but there's this interesting Eddie, your resume, where you worked as a scientist on set on the TV show The Biggest Loser. What were you doing?
Yeah, so that's while I was still at NIH, and I was really interested in understanding what was happening to these folks. This was a very strange lifestyle intervention that was televised on national TV for many, many seasons. And these folks were, subject to a whole lot of abuse, but in the space of that abuse, they were doing a ton of exercise, different kinds of exercise. And it wasn't clear how that crazy lifestyle intervention was influencing their bodies in terms of how much of the weight that they were losing was coming from body fat versus muscle, for example, or whether or not their metabolisms would slow down, as typically happens with diet programs that don't involve a lot of exercise. There was a lot of discussion back then that exercise would boost metabolism, and therefore you wouldn't experience the usual metabolic slowing. So I was interested in participating as a researcher, observing these folks who were doing this sort of natural experiment, a study that couldn't have been done otherwise had they not already been signing themselves up for this kind of abuse on a national television show.
What did you learn?
Yeah, we learned that many of the things that we had presumed about exercise and about metabolic slowing didn't turn out to be true. So despite the fact that these folks were engaging in roughly 3 hours of vigorous exercise every day of the week, their metabolic rate did slow down by a average. But maybe most surprising, greatest slowing of metabolism who lost the most weight. And this was a trend that we saw kind of 6 years later when we brought these folks back to the NIH Clinical Center to study them 6 years after the lights of the television cameras turned off. Most folks had regained most of